So now that we have an understanding of our substrate types, our solvent types, and the relative strength of a base, we're finally ready to talk about the nucleophile, which is going to be more complex. A nucleophile will sometimes follow the trends of basicity, but depending on the solvent, it might grow stronger or weaker. So we're going to need to factor in a few different ideas in order to understand the strength of a nucleophile. The strength of a nucleophile does depend on certain situations. We're going to look over 4 qualities that will determine the overall relative strength of a nucleophile. But first, we need to talk about what is a nucleophile. Well, nucleophile can be broken down into 2 words. Nucleo, which is nucleus, and phile, which means loving. Like if you've ever heard the term cinephile, it's someone who absolutely loves movies and cinema. A nucleophile is a chemical, whether it be a molecule or an atom or an ion, that particularly loves a nucleus. And it's going to be because that nucleus is where the positive charge is stored. So what we're going to be seeing in our reactions is we'll most often see something like, let's say, a carbon bonded to a bromine. There's some other stuff going on here, but across this bond, we would have a dipole, and that carbon would have a partial positive charge. So that carbon is going to be the nucleus that the nucleophile is attracted to. So that's what we're really looking at. What are the qualities that make something attracted to a positive dipole like this? The first quality of the strength of a nucleophile is going to depend on charge. And a way you can think about this is that the conjugate base of something, which is always going to be more negative because it would have lost a proton to become a conjugate base, the conjugate base is always a better nucleophile. All right? So the conjugate base is always a better nucleophile, and the more negative charge a molecule has, the stronger the nucleophile. We can think of that this way. If I've got that carbon that has that positive dipole, what's going to be more attracted to that positive dipole? We could say the negative dipole of a water molecule, or the straight up negative ion of a hydroxide. Or better yet, the -2 anion of pure oxygen. That's going to be way more attracted to that. So we can see that that charge is going to pull that nucleophile in more. There's going to be a greater force there. So charge is our first thing. The next major factor in the strength of a nucleophile is electronegativity. And this is going to follow the same trend as basicity. The reason for that is that a base is really a subset of a nucleophile. It's going to be this specific nucleophile that's attacking hydrogen. Okay? So when we're talking about bases, we're talking about a nucleophile that attacks hydrogen. So a nucleophile in general is going to attack any positive charge. In our context, it's often going to be carbon. But that same trend of electronegativity is going to persist. The reason is that since it's trying to attack that nucleus, it's trying to go after that positive charge, if it's stable with a negative charge, then it's not going to go after it. So we need something that is not happy with a negative charge. So the higher the electronegativity, the lower the nucleophilicity. Now this is going to work across the top of the periodic table. So this is going to be just like in bases. I'm going to draw CH3 minus is going to be a greater nucleophile than NH2 minus, which will be a greater nucleophile than OH minus, which is still greater than F minus. Okay? So it's the same trend. But what about up and down the periodic table? What about comparing fluorine, chlorine, bromine, and iodine? Let's look at the next trend. So remember, we have 2 types of solvents, a protic solvent and an aprotic solvent. A protic solvent is going to have hydrogen bonding. An aprotic solvent will not have hydrogen binding. So how is that going to affect us going up and down the periodic table? Well, when we have that hydrogen binding, it's going to be really easy for, let's say we're using water, which has hydrogen binding. It's going to be really easy for those water molecules to cluster around something like fluorine, which has a really high electronegativity. It makes it really good at pulling things in. However, iodine, because it has its charge all spread out around a really large atomic radius, ionic radius in this case, is not going to participate in hydrogen binding as well. And so because of that, in a protic solvent, it's actually going to be easier for iodine to get to the nucleus, where fluorine is going to be constantly interacting with all of those hydrogen bonds, all of those water molecules that are surrounding it. It's like it's a cool kid who's trying to move through a party, and every time it hits someone else, they've got to stop and have a conversation. Well, It's trying to get across the party to get to the girl, but it's so cool. So all of these other molecules are interacting with it as it tries to go along, and it takes forever to get there. Where iodine can move right through. No one wants to talk to iodine. So it gets right through the party, goes straight for the girl. In this case, iodine is going to be able to go straight for the nucleus. But that is only in a protic solvent. So let's write that down. We've got protic solvent and a protic solvent. Our nucleophile strength is going to go down the periodic table. However, if we don't have that hydrogen binding hindering the progress, then we're actually going to follow that same basicity trend. So in an aprotic solvent, we're going to be going up the periodic table. Now, why is this different? Well, if we think about it, in a protic solvent, that basicity strength, that strength of the base, is going to be pulling at those hydrogens. Well, we're not trying to attack a hydrogen when we're doing organic chemistry. When we're trying to run with a nucleophile, we're trying to attack a carbon. So the hydrogens are getting in the way. So the same thing that made it a strong base in that case makes it a weak nucleophile. So that's why that trend follows that way. So let's write that down. And I'm going to write that in black because apparently the green isn't showing up that well. So in a aprotic solvent, nucleophile strength follows basicity. In a protic solvent, nucleophile strength goes in the opposite direction of basicity. Or we'll say nucleophile strength increases going down the periodic table. But what if we don't know what the solvent is? What if we're not told the solvent? There are going to be a lot of cases like that. If you aren't told the solvent, assume the solvent is water, because water is so common in the use as a solvent. We do so many things in aqueous solution that we can kind of just assume that if we're not told something different, it's going to be a protic solution of water. Okay? So we're going to more often run into a protic solvent. The final piece that factors into the strength of a nucleophile is steric hindrance. If the nucleophile is too big to get to the carbon or whatever it's trying to attack, it's physically unable to react, and it's going to take a lot longer to react. So steric hindrance is the size of the nucleophile. As the size of the nucleophile increases, the nucleophile strength decreases. So now that we have all four major pieces of nucleophile strength accounted for, we should be able to see that nucleophile strength is not necessarily just a quality of a molecule. It is going to depend on the situation. So nucleophile strength is a contextual quality. We'll have to consider the surroundings of a molecule in order to determine if it is a strong nucleophile. So your next assignment is going to be ranking the strength of nucleophiles so that we can get really good at determining these steps, at determining this quality.